Hi, I'm going to present the paper about decoupling cores, kernels, and operating systems. This paper presents Barrelfish DC, an extension to the Barrelfish OS, which decouples physical cores from native OS kernel, and furthermore, the kernel itself from the rest of the OS and application states. In Barrelfish DC, native kernel code on any core can be quickly replaced. Kernel states move between cores, and cores added and removed from the systems transparently to applications and OS process, which continue to execute. Before going to present about whole parts of the paper, I would like to give a short outline about this paper, about this presentation. First, I will introduce about the motivation in trends in hardware and software. And then I will present about the implementation on booting and shutting down cores dynamically. The rest of the paper, which about evaluation and conclusion, will be given by my partner. So first, what's happening to hardware? Today we are mostly constrained by power consumption. This will bring us, for example, reconfigurable cores, which means we can dynamically change behavior. So this is we already do today, like DVFS, which stands for Dynamic Voltage and Frequency Scaling, and Turbo Boost and SMT. Also, there's some research technique, such like core confusion, which allow us to fill cores multiple physical cores into simple, more powerful cores or speed them up again. On the other hand, the future may have to do dark silicon, which means we can have many cores, but we cannot power them all at the same time. So what that means for us? For adding and removing cores in the system? Well, we already do it today. For example, if course fails or if reallocate course to different machines. On the other hand, you may take cores out of service because we will not power them all at the same time. Also, there's heterogeneous cores in our machine, giving us asymmetric performance. And for example, one such logical conclusion of this would be conservation cores. Now we imagine that we build an OS in a dark silicon area. So you have set a heterogeneous cores and you need to switch between the cores based on your workload. But you also need to power down and take cores out of service because you don't have the power to power everything at the same time. So this is the current model today. The kernel running as a single program in all cores, and every cores run the same code, as it's hard to adapt like heterogeneous cores. So what happens if you move a core in such a system? Well, we have to go deep to the data structure to reflect this change. Typically, this requires global coordination, and also at the data structure may be global share protect by locks. What happens if processor holding on the locks? So this is a lot of issues there. So what's happening to software? In software, we usually need to adapt to different work in our OS. Now, general purpose kernels were very useful to adapt, but we still have to adapt to modify build, boot, and runtime. For example, to facilitate debugging with profiling and tracing. And sometimes application requirements are very strict, such as real-time support, and it's hard to adapt everything into general purpose kernel. Now, there are also research techniques that works by modifying or upgrading cores on the fly, as is the case, for example, ksupplies in Linux or K42 update mechanism. So we argue that a good architecture model dealing with dynamic cores or adapting to heterogeneous cores on or changing software requirements is a multi-kernel model. In multi-kernel, each core runs separate kernel program, and state is currently in per-core states into what we call OS node. Now, we have to run applications on top of that, and applications may share state between cores. Therefore, we replicate states between cores using asymmetric message passing. So, however, a multi-kernel model is not enough dealing with dynamic cores, so we still need to deal with OS node. So, therefore, we use a basis which Barrelfish DC or Barrelfish OS is an implementation of multi-kernel, and we add some features to Barrelfish DC, which I mentioned at the beginning. Treat cores as much as possible as plug device. So we'll next love how we're booting a core dynamically with boot drivers and how we shut down a core in system. We use a technique that externalize kernel states that allow us to decouple cores, kernels, and operating systems. So, and we should mention before that in this paper, they only focus entirely on mechanism, and so do not address scheduling and the policies for kernel replacement, kernel power management, or application migration. Note also that the paper's main motivation in Barrelfish DC is adapting the OS for performance and flexibility. And so this paper doesn't consider about fault tolerance and isolation. So the first is booting a new core. Bring a core online is a question of turning on, updating this table, and creating per core states when needed. Previous version of Barrelfish also adapted this approach and booted all cores during system initialization, though there has been experimental work on dynamic booting of heterogeneous cores. Barrelfish DC targets a broader hardware landscape with complex machine comprising potentially heterogeneous cores. Since Barrelfish DC runs a different kernel instance on each core, there's no reason why the same kernel code should run everywhere. So we need an OS representation of a core on machine, which abstracts the hardware-dependent mechanism for bringing the core up and down. Therefore, Barrelfish DC introduced the concept of a boot driver, which is a piece of code running on the home core, which manages a target core and encapsulates the hardware functionally to boot, suspend, resume, and power down later. Currently, boot drivers run as processes but closely resemble device driver and could equally run as software objects within another process. And these are the 5 steps. A new core is brought online as follows. First, the core is detached by some platform-specific mechanisms and its appearance registered with the device management subsystem. And then Barrelfish DC select and start appropriate boot driver for the new core. The third step is Barrelfish DC select a kernel binary and an argument for the new core and direct the boot driver to boot the kernel on the core. The next step is the boot driver loads and relocates the kernel and executes the hardware protocol to start a new core. The last step is the new kernel initialize and use existing Barrelfish protocol for integrating into running OS. Booting a core in Barrelfish DC only involves 2 processes, the boot driver on home core and the kernel on the target core. For this reason, we require no global locks or other synchronization in the system, and the performance of these operations is not impacted by the load on other cores. Shutting down a core. Shutting down a core is much harder than booting because we need to deal with per core state. We need more space to deal with the scheduler queues memory pools, and also the page tables. So it will take much time and energy. However, we want to remove the core as fast as possible. The general approach they follows just get state out of the way quickly or just dismantle it later or lazily. So how does it work in our OS in Barrelfish DC? First, close them away, and we are able to capture this OS node or all per core states, and we move it to a different core. Now, we add an OS scheduler into kernel that is able to dispatch different OS nodes. And we call that this core, and we call this case that one OS code to remove to a kernel that already have an OS node, temporarily parking OS node. And we can already notice that this approach is highly scalable as we only evolve 2 cores in process right now. We don't need to normally coordinate it into system. So what happens next? We can either move back to previous course or move it somewhere else. So what is OS node? And how do we capture this OS node? It's typically not clear in OS per core states. It's not explicitly defined and typically have many different data structure. So in this paper, we use partitioned capabilities systems to explicitly capture OS nodes, meaning entire per core states in a single data structure. I will introduce about the part of the partitioned capabilities. Capabilities are typed to reflect what the memory is used for. So a frame capabilities refers to memory that the holder can map into their address space, while a C note capabilities refers to memory that is used to store the bit representation of capabilities themselves. This captures all exciting information and memory allocation about applications. So all per core states in the kernel are now be accessed to the structure or reconstructed from the capability tree. We still need to be able to reach this and the structure and pass it around in our system. Therefore, we add KCB or kernel control block. KCB combines some states that don't need to persist across a kernel start. KCB is also a capability itself, means we now have a representable handle in systems to move entire per core state or out. So this method of state externalization and dynamic core booting is much more general mechanisms because we are now able to move the per core state around internally in our system, and we can also replace the kernel dynamically on needs of the OS. Also, I want to talk about interrupt and how can we deal with the interrupts. In general, interrupts they distinguish to 3 types of interrupting in system. First, like handle local 2 cores and the CPU driver, like timers, and interprocessor interrupts which send between OS nodes, and also the device interrupts. So what happens if you have a device that runs on some cores and is migrate to different cores? Right now, we initially mask all interrupts on the core, and then we have to register the interrupts on device driver. So we typically doing this process is sometimes happening between and you have to go and check again if something happens into device, or you can pull the device while you are doing this shift. As the part of the evaluation section, we are going to show how it's actually do this and how fast it is. So welcome to my partner.
We present here a performance evaluation of Barrelfish. First, core management. We measure the performance of starting and stopping cores in Barrelfish and in Linux. Second, applications. We investigate the behavior of applications when we restart kernels and when we park OS nodes. Third, performance isolation, specialized kernels. We demonstrate isolating performance via a specialized kernel. Fourth, kernel updates. While performing this evaluation, hyperthreading, turbo boost, and speed step technologies are disabled in machines that support them, as they complicate cycle counter measurements. Core management options. In this section, we evaluate the performance of managing cores in Barrelfish and also in Linux using the CPU hot plug facility. We consider two operations, shutting down a core and bringing it back up again. Bringing up a core in Linux is different from bringing up a core in Barrelfish. In Barrelfish, each core executes a different kernel which needs to be loaded by the boot driver, while in Linux, all cores share the same core. Furthermore, because cores share state in Linux, core management operations require global synchronization, resulting in stopping application execution in all cores for an extended period of time. Stopping cores is also different between Linux and Barrelfish. In Linux, applications executed in the halting core need to be migrated to other online cores before the shutdown can proceed. While in Barrelfish, we typically would move a complete OS node after the shutdown and not individual applications. Stopping cores. The cost of stopping core in Barrelfish is about 0.8 microsecond. Barrelfish does not share state across cores, and as a result, no synchronization between cores is needed to shut one down. The cost of shutting down a core in Linux ranges from 46 milliseconds to 131 milliseconds. More importantly, the shutdown cost in Linux explodes when applying load, while it generally remains the same for Barrelfish. For example, the average time to power down a core in Linux on Haswell machine is increased by 55 times when we apply load. For Barrelfish, the setup cost in boot driver dominates the cost of starting a core. The figure shows a breakdown of the cost for bringing up a core on Haswell machine. Barrelfish has to prepare the kernel image when idle. The cost of bringing up a core for Barrelfish is similar to the Linux cost. Applications. In this section, we evaluate the behavior of real applications under two management operations, restarting, where we update the core kernel as the application runs, and parking. In parking, we run the application in a core with a normal kernel and then move its OS node into multi-KCB kernel running on a different core. While the application is parked, it will share the core with another OS node. First, Ethernet driver. In this experiment, we use ping command from a client machine to send ICMP echo request to the NIC. The figure shows the effect of the restart operation in the round trip latency experienced by the client. Initially, the ping latency is 0.042 milliseconds on average with small variation. Restarting the kernel produces two outliers, packets 2307 and 2308 with an RTT of 11.1 milliseconds and 1.07 milliseconds respectively. When parking begins, we observe an initial latency spike from 0.042 milliseconds to 73.4 milliseconds. The spike is caused by the parking operations, which involve sending a KCB capability reference from the boot driver to the multi-KCB kernel as a message. After the initial coordination, outliers are only caused by KCB time sharing. After unparking the driver, latency returns to its initial level. Unparking does not cause the same spike as parking because we do not use messages. We hold the multi-KCB kernel and directly pass the KCB reference to a newly booted kernel. Second, web server. In this experiment, we examine how a web server that serves files over the network behaves when its core is restarted and when its OS node is parked. We initially transfer on client machine in the server's LAN using wget command and plot the achieved bandwidth for each 50 kilobytes chunk when fetching 1 gigabyte file. The figure shows the result for the kernel restart experiment. The effect in this case is negligible on the client side. Parking leads to number of outliers caused by the KCB time sharing. During parking, the average bandwidth is slightly lower with a higher standard derivation. Third, PostgreSQL. We run a PostgreSQL database server in Barrelfish using TPCH data with a scaling factor of 0.01 stored in an in-memory file system. We measure the latency of repeated CPU-bound query. Before rebooting, average query latency is 36 milliseconds. When a restart is performed, the query has latency of 51 milliseconds. After a few queries, the latency returns to its initial value, shows the effect of parking the OS node that contains a PostgreSQL server. When the kernel is parked, we observe two sets of outliers, one with a latency of about 76 milliseconds and one with a latency close to 56 milliseconds. This happens because depending on the latency, some queries wait for 2 KCB time slices of the co-hosted kernel, while others wait only for one parking. As expected, causes a performance degradation, especially for a latency critical applications. Furthermore, with improved KCB scheduling algorithms, the performance degradation can be reduced or tuned. Kernel update. First, we shut down the target core. Then we reboot the core with a new kernel image and passing it to the previous OS node. From an application perspective, this will just look like the application has not been scheduled for a while. To evaluate the use case, we have running PostgreSQL with TPCH database inside the OS node, and we measure latency of queries on y-axis and query over time on x-axis. At some point, we hot swap the kernel and see this produces some outliers because we actually need to reboot the core, so outliers are all about 10 to 15 milliseconds. Specialized kernels. To evaluate a real-time application use case, first we shut down the core, then we're going to move OS node and temporarily park it on another core. So we can now free up space on the core. So here we again have a PostgreSQL instance with a TPCH database inside an OS node. And on the first part, we have one OS node per core, and the response time is about 40 milliseconds. At some point, we temporarily parked OS node. Currently, OS node share time on the core, therefore the latency increases up to 80 milliseconds. Afterwards, we move OS node back to its original core, and the query response time normalizes again. Now we have freed up one of the cores. We can boot this core with special kernel and build a simple real-time kernel that essentially does not take any interrupts. It does not have any timer or scheduler in the kernel. It is designed to just run single application. So this kernel constructed on OS node and temporarily run a real-time application. To evaluate the performance isolation that can be achieved with a specialized kernel compared to the isolation provided by an unmodified Barrelfish kernel and Linux 3.13 kernel. To measure OS jitter, we use a synthetic benchmark that only performs memory stores to a single location. We sample the timestamp counter every 1000 iterations for a total 1 million sample. This figure shows a histogram of sample cycles where for all systems, most of the values fall into the 6 to 7,000 range, that is 6-7 cycles latency per iteration. The Barrelfish dedicated kernel where all the samples are in 6,000 to 7,000 range. In Linux and Barrelfish, we observe significant outliers that fall outside this range. We conclude that Barrelfish enables the online deployment of a dedicated, simple-to-build OS kernel that eliminates OS jitter. Future work and applications. OS nodes are an entire per core state. If you want to move between power efficient and high performance core, as a kernel developers interested in dynamic OS instrumentation, for example, profiling, tracing kernels, which we can simply do now by swapping kernels with a debug kernel. Also to test impact of some features having the kernel can simply swap kernels to do A/B kernel testing. Specialize kernel to run application in guess ring 0. With this method, it can simply run this Arrakis OS on some of the core and move it back later. Conclusion: Barrelfish presents a radically different vision of how cores are exploited by an OS and the applications running above it, and implements it in a viable software stack. The notion that OS state, kernel code, and execution units should be decoupled and freely interchangeable. Barrelfish is an OS whose design assumes that all cores are dynamic. As hardware becomes more dynamic and scalability concern increases, the need to partition or replicate state across cores, system software will have to change its assumption about the underlying platform. For many versions of dark silicon hardware, this may be the only way for system software. Thank you.